I don't know if we're going to get audio on this or not. We'll find out. So B, give an example other than X itself of a proposition generated by P, Q, and R that's equivalent to X. All right, so we want another proposition that's equivalent to this. Okay, so logical equivalence, we can use our identities, and we can do that to basically simplify an expression, change it into another form. So, so what did people do for this? Because I know some people got solutions. Distribution, right? So we know that we can take something ORed with R and P, and that's equivalent to something ORed with R and the same something ORed with P. So we can distribute this OR inside. So the something in this case might be P and not Q. So P and not Q, ORed with R, ANDed with P and not Q, ORed with P. And we can distribute again because we have an AND with an OR. So P and not Q ORed with R is P and R, ORed with not Q and R. Sorry, P or R, ANDed with not Q or R. All ANDed with this stuff, which is P or P, ANDed with not Q or P. And P or P is just P. So we've got P or R, ANDed with not Q or R, ANDed with P, ANDed with not Q or P. Well, that's a different expression, but it's equivalent. But I think we could factor out the R from these if we wanted, or we could factor out the not Q from these. And so you can start changing this around into different expressions, right, and find something that's equivalent to it. And the goal is just, to find something other than X is equivalent to X, right? Find some other expression. But questions C and D are the ones that are a little more confusing, perhaps. So question C says, give an example of a proposition other than X that implies X. So we want some proposition P. I'll switch back in a minute. Find a proposition P such that P implies X. Right? And remember, X is P and not Q, ORed with R and P. So you want some proposition P so that if P is true, this is true. And it's not equivalence. We're not looking for something that's equal to X. We're looking for something that if it's true, then X is true. All right, Connor.
Because there are two different expressions or together, if one of the expressions is true, would X be true?
Exactly. If we were to just simply write, for example, R and P, looking at this, we know that if R and P is true, then X must be true, because X is the OR of true with something. Doesn't matter what this something is. If R and P is true, X is true. So that would be one answer for that part. Same thing, P and not Q would also be something that implies X. All right, so here we're finding a P that implies X. The next part of the question is find some Q such that X implies that proposition. So find something that has got to be true if X is true. How about P? If X is true, this AND must be true which means in particular P must be true, right? Or none of that, but this would have to be true, which is an AND, which means that P has to be true. So the only way X can be true is if P itself is true, right? So if P is, if X is true, then we know that P is true. This is the little p up here. So that would be a proposition implied by X. So again, this is one of these things where there's no method to finding this answer. It's about sort of exploring the expression X and thinking about what it means and what happens if certain parts of it are true or false, and waiting for the answer to kind of pop up. Mm-hmm.
Separate question. How would you demonstrate 0 in a proposition?
What do you mean by demonstrate 0?
Well, it asks to pick certain things from the list of propositions, and some of those propositions have 0 in them.
Oh, okay.
How would you write that out using words?
Well, I'm not sure. So let's look at P or false is equivalent to P or 0, right? So I could say something like P is the proposition, today is Friday. And I'm going to actually make F a proposition that's false. Let F be the proposition. I shouldn't do this, but I'm going to do it anyway. F be the proposition 1 plus 1 equals 3, which is equivalent to false. So P or F is the proposition, today is Friday, or 1 plus 1 equals 3. And is that proposition true or false? It's true, right? But if I change P to the proposition, today is Sunday, this says today is Sunday or 1 plus 1 equals 3, and is false. And it's just kind of a demonstration that the truth value of this proposition, P disjunction with F, is the same as the truth value of this proposition, P. So something like that.
So the 0 and false are interchangeable.
Yeah, the book uses 0, I think, and I tend to use false, but sometimes I slip into 0 too. Yeah.
For 3.4, question 2, can you kind of go through what you would do? Because I wrote out a truth table, and I'm not fully sure how you would want us to go about solving this.
So I would hopefully give you more instruction than that, but show that the common fallacy, P implies Q, not P, therefore not Q. Show that this is not a law of logic. So do you remember what this fallacy is called?
Fallacy of supporting,
Denying the hypothesis, right? Because that's what, so this P is the hypothesis, Q is the conclusion. And what we're doing in here is we're saying the hypothesis is false. And then we're getting a fallacy.
Switch to the talk.
Thanks.
Yeah.
So hypothesis conclusion, we're saying the hypothesis is false, and that's where our fallacy follows from.
Okay.
So what's an example of this? Well, pick some propositions P and Q for which everybody understands that this is true, and everybody understands that this is true, but everybody understands that this conclusion is false. Right? That's one way to sort of show it. A rigorous way to show it would be a truth table. Right? That would be a perfectly fine way to show it. But I would probably say either, demonstrate this using a truth table or laws of logic, or I would say, demonstrate this by assigning specific propositions to P and Q and showing that it's a fallacy. So a typical example might be let P be the proposition. Let Q be the proposition. If you spend 20 hours per day on CSE 215, it's not an if. You spend 20 hours a day on CSE 215, and Q is the proposition, you get at least a C. And let's suppose that that's true, because if I see you spending 20 hours a week on discrete structures, you're probably going to get a C, right? So if P then Q is absolutely true, okay? And the second line is saying you don't spend 20 hours a week on CSE 215, 20 hours a day on CSE 215. And the conclusion here is you're not going to get at least a C in the course, right? And that's not true. You can get an A with less than 20 hours a day. In fact, you'll probably do better because you'll get more than 4 hours of sleep. So that could be a demonstration of a fallacy.
What about the question, the one that was 4B?
Same section?
No, on section 2.8.
3.0, good quantifiers.
It asked about mothers, or
Yeah.
that one was kind of.
Yeah, that one's interesting, right?
I couldn't answer that one. Yeah.
So let me just copy these down here. M of xy is the proposition that x is the mother of y, right?
And universe, so
Yeah. All right, so particularly looking at B?
yeah.
Okay, so so we're asked to write the statement, everyone has a grandmother. Using quantifiers. Does it ask us to write everybody has a mother? I think that's one of the first ones. But how would we write the statement everybody has a mother using this proposition? This is a proposition. It's got two variables, but it's a declarative statement, right? So how would we write everybody has a mother? How can we just rephrase that statement in terms of there exists or for all? For all?
For all x of mx, y, there exists an x.
So how would we put it in words? Forget propositional calculus for a moment. How do we just describe in words that everybody has a mother?
People,
For all people,
there exists a person.
there exists a person who is their mother, right? So for all people, there exists a person such that M is the mother of that person. So that's the propositional logic version of everybody has a mother. All right, for all people, you can pick any person you want, that's P. We can find some person M who is their mother. Okay, well, to say that there's a grandmother, we could also say, and there exists a person G such that G is the mother of M. So this says for any person you pick, you can find a mom, and you can find a grandmother who's the mother of that mom, which means that they're the grandmother of person P. And normally we put these quantifiers in the beginning, so I could rewrite this a little differently. For all P, there exists M and G such that M of M comma P and M of G comma little m. So that would probably work. right? So this was part one of that question. What does that say in English?
There exists a person that is the mother of all people.
Yeah, there exists an M such that for any person we think of, M is the mother of that person. So there's like a universal mom. Yeah. What does that say? Not quite. Go straight from this verbatim. Don't try to analyze it.
There exists a person who is their own brother.
Yeah, right. There exists an M. There's some M we can find, at least one, such that that M is the mother of that M. Right, so there's somebody who is their own mother. Which could be like a planaria or something, I suppose, because they divide that way. Right? So we can write nonsense, right? But the goal here is, to get comfortable with quantifiers and going back and forth between the imprecise world of English and the more precise world of propositional logic, right? Because our word problems start off in English, and first thing we got to do, put them into the language of propositions. All right, good. All right, so you have asked a sufficient number of questions so that I will not collect the homework. Yay. Good job. What? It's not. It's for your own information, but I will give you a homework question at the end of today that will be due on Monday. Okay, and it'll be a proof type question.
So we never can use it?
You don't have to turn it in. Okay, and we've been doing things on the board, but I'm changing it up today, so I'm just going to go through some of the stuff on proof. So questions on the lectures. All right, last lecture was about proofs and methods of proof, and we talked about direct and indirect proofs, and we got into even and odd numbers.
Is there some sort of quick way that we know what sort of direction we should be taking with the proof, like direct or indirect?
Not really.
So it's just kind of think it through a little bit.
But
Thinking that same thing too.
a really good problem set, and I think I gave you these, is at 3.5, question 3. So it asks for direct and indirect proofs of these. Question 4, direct and indirect proofs of these. Those are really good to work on. Okay. And I'm going to say, let's just say right now, write those up for turning in on Monday. So section 3.5, numbers 3 and 4.
Will you be putting those on Canvas?
Yeah, I'll post it since a lot of the class isn't here. Give them a break. So write those up and turn them in Monday. But let's do some of these. Let's do this first one together. So this is written out as follows: A arrow B, comma C arrow B, comma D arrow something, comma D, double arrow B. Okay. Let me tell you how to interpret this, because if you interpret it wrong, then you don't get the right answer. All right, so this is what we're trying to prove. This is how we would write this in this equation form that we've been doing. There are 4 propositions here on the left. Okay, the first proposition is A implies B. The second is C implies B. The third is D implies A or C. The fourth is D. The double arrow says everything to the left implies the thing to the right. And we write that as everything to the left listed here implies the thing to the right.
It doesn't go the other way around, right? B doesn't.
Doesn't mean that B implies the stuff on the left, no. It's directional. And there's nowhere here that it says D implies B, okay? This is breaking things up. So here's the 4 hypotheses, here's the conclusion. Okay, so first thing I would do is write it into this form because it's less chance of confusion. And if you want to do a direct proof, you kind of stare at these and you say, is there any way that I can get B from these things? Right? Direct proof, we start with what we know, which are the hypotheses, and we try to get the conclusion. Well, we're trying to get B, and these are the only 2 statements that have a B on the right side. So if we could prove A or we could prove C, that would either of those would give us B, right? Well, there's one thing we're given that has A and C on the right, and this says that if D is true, then either A or C is true. And there's only one thing with D, but that tells us D is true. So now we're getting the little light bulb that's saying, oh wait, if D is true, then A or C has to be true. And if A is true, B is true. If C is true, B is true. Okay, so D will get me to B. So now we believe this. And now you got to go through and you got to formalize that, right? Court of law, you're going to bring this into a jury and try to explain to them why B is true. And you can't say, well, just look at it, it's obvious, right?
So we start by saying D is true.
Start by saying D is true, sure. We can say D, and I'm going to number these steps. So D is true, and what's the reason why D is true? It's a hypothesis. It's a thing we've been given. Well, what do we do with D? Why was that useful to list?
Because D goes to A or C.
Because D goes to A or C. That's statement 2. Why is that true? That's a hypothesis. And then, say again?
A or C is
A or C is true. Why is that?
because from D is true, therefore one of those has to be true.
Okay, so the short version of that, direct reasoning. So look in the book, page 59, and it's got the fancy names for all of these things. And this one's called direct reasoning, and I'm going to list the pieces that I fed into that identity, which was statements 1 and 2. So A or C is true. Now at this point it's tempting to say, well, if A is true, then B is true. And if C is true, then B is true. And one of these has to be true because the OR is true. And we're not doing propositional logic at that point. We're arguing, right? The judge will say argumentative. Yeah.
Substitution.
Okay, what should we substitute?
A to B.
What do we substitute it in?
Inside the A or B. A or C.
Well, that's the right idea, but I don't know how to do that. Because A is not equivalent to B, right? A implies B.
Where is B?
Can we write what? Closer.
Can you combine A or C implies B? Can you do that?
What would that follow from?
If you read it backwards,
Well, A implies B and C implies B, but I don't think we have a theorem that says if we take A or C, that's going to imply B. But we can get there. But the issue is we've got these arrows here and we've got these OR symbols here, right? If we could get rid of these arrows, our life might be a little easier. And there's a way to get rid of arrows and replace them with like ORs and NOTs. Remember that identity? So we can do conditional equivalence. So let's say A implies B. That's a hypothesis. And let's write the equivalent of that, which says either A has to be true, either B has to be true, or A has to be false. That's conditional equivalence. I think that's what it's called in the book. So if A is false, that conditional is true. If B is true, the conditional is true. And you can write out, we did this on the board, we wrote out the truth tables for these, and they're exactly the same. And 6, we can do C implies B. And 7, we can do not C or B. And where was I going with that? I don't remember. Well, let's combine this. We know that 5 is true, we know 7 is true, so you know the following is true. Not A or B, and not C or B. And that's just a conjunction of 5 and 7. And now we're going to distribute the heck out of everything. So this thing ANDed with this thing, and I think I'm just going to FOIL it maybe.
Pull the B out.
That would probably be the best option, because then you could put the A and the C in one expression and replace that expression with the one at the top. So then it would be B. Oh, but that's an implication of,
Oh, yeah. Let's see. I don't know, let's brute force it. We got a few minutes. Let's see where this gets us. So this thing ANDed with this. So not A or B, ANDed with not C. And that's ORed with not A or B, ANDed with B. And so this is not A and C, not C, or B and not C, or not A and B, or B and not B. Got a better idea?
Because B is ORed with both and not A and not C. Could we say B or A and not C? Not A and not C?
Like that?
Yes.
That's probably better. Okay, so forget my approach, use Connor's. Right, so pull out the B. So this is B ORed with not A and not C. All right, so that's just pulling the distribution in the other direction. And so this is B OR, and not A and not C, let's use De Morgan on that. And this is not A or C. That's De Morgan's theorem. And we know A or C is true, so this is B or not true. That's substitution. And so this is B or false. And B or false is just B, which was what was to be shown. So typically you do this, you make some missteps maybe, you go down some dead ends, maybe you make some mistakes, but eventually, right, we figure out what the steps are, and then you write that up nice and neatly, right? And that's what you can turn in. Because it's not an exact process, right? It's really a trial and error. Okay, so that's a direct proof. What is an indirect proof?
Start with a case where the assumption is false.
Start with a case where the assumption is false, okay? Where the conclusion is false, and try to argue to a contradiction. And let me show you what is not an indirect proof. So an indirect proof, we're going to start off, and we're going to suppose, so let me write all these down again. A implies B, C implies B, D implies A or C, D, and we're trying to conclude B. Okay, so to do a proof by contradiction, we start off by assuming not B. That's an assumption. And we're going to argue until we get a contradiction. And once we reach a contradiction, we're going to know that not B implies false, right? Implies a contradiction, and so not B can't be true, so B must be true. But don't do this. Start off with not B, do all of this, prove B, and then say that contradicts not B. Okay, that's really a direct proof. Okay? And it's easy to feel like you're doing an indirect proof, okay? But the idea is to start with this and somehow argue to a contradiction, like not D, or C does not imply B, or something like that.
So you want us to start with D, not B.
I want you to start with the contradiction of the hypothesis, the negation of the hypothesis. Right, we're trying to show B, right? So we start off and we assume B is false, but that all of these things are true, and we're trying to find a problem. Well, if B is false, and we know that A implies B, we can conclude A must also be false. That's just a contrapositive. A implies B, but B is not true, so A cannot be true. And C implies B, but B is not true, so C cannot be true. So we have not A and not C. And we can use De Morgan's and say, therefore, we do not have A or C. But we know that D implies A or C, and A or C is false, and therefore we have not D. But we also have D. And so we have not D and D being true, and that's a contradiction. And since we know these things are true, and we use logical reasoning, and we came up with a contradiction, the only possibility is that this thing, which we didn't know was true, must in fact be false. So not B is false, B must be true. So that's an indirect proof. So try those questions 3 and 4. Okay, here's the first one. And the indirect proof is a fair bit simpler than the direct one in this case, right? The direct one felt like a lot more manipulation of symbols. Sometimes an indirect proof is easier, sometimes a direct proof is easier. And in the video, we started proving things about if n is even, then n squared is even, or if n squared is odd, then n is odd, right? And those are examples of where one direction's easier than the other. Sometimes direct, sometimes indirect. All right, so I've already posted the lecture and homework and stuff for Monday, which is a new unit. It's on number theory, but I still want to spend some more time next week talking about proofs. So I want you to work on these, write them up, bring questions. I'll collect 3 and 4, and we'll spend some time on the board doing some other proofs. Okay, because I want to make sure everybody's got experience going through this, and I want to see how you're reasoning. And possibly later on Monday, but probably by Wednesday, we'll start talking about number theory. So go ahead and watch that video, take the quiz, think about the homework, but we may not start talking about number theory till Wednesday. We may get to it Monday, we'll see. All right, I'll see you next week.